you want to cut and paste in. I've got all the answers there. Okay? Okay, so Lou's going to do the first part of the presentation, mostly on control logic.
Hi, let's get started.
Speak loud, Lou.
Okay. So this lab, we're going to cover basically three things. The first one is how to use if statement. And the second one is more information on how to use functions. And the third one is the introduction to LU factorization, which you can have a better understanding of the homework. And let's go to the first example, the if statements. If statements is like a control flow in the Julia language. And it's also commonly used in other programming languages. It's very like the for statement we covered in lab 2. Those statements are used to regulate like the order of the statement to be executed. So the common way to use the if statement is using this syntax. The keyword if and follows a condition. This condition will be evaluated as a true or false. And if this condition is evaluated as true, the statement 1 gonna be executed. Otherwise, it will ignore the statement 1 and directly goes to the statement 2. So let's see the example. We define x equals to 1 and y equals to 1. So the if statement is the keyword if follows the condition. Here is the x is less than y. So when we run this if statement, it's gonna evaluate this condition first. So currently the x is not less than y. So this will be evaluated as false. So this is false, then the line 5 will not be executed. So it directly executed the line 7. So we can see it prints this line x is no less than y. So we can see we can print this x minus y, x is less than y. It is evaluated as false. So this statement is not executed. And if this if else only has one condition to be evaluated. But if we want to have more conditions which we want to split, which we want to consider more conditions in one if statement, we can use if, else if, and else, this statement. And for this else if, you can use as many as else if as you want. The syntax will be this condition 1 to condition n, and which corresponds to a statement. So it will evaluate the conditions one by one until one condition is evaluated as true, and it will not evaluate other conditions after that is true. So in this case, if the condition 1 is true, it will not evaluate any of the condition 2 or condition 3. It's just only executed the statement 1. So, for example, the same example as before. Previously, we can only know if x is less than y And right now we can see, use the else if, we can see if x is no less than y, we can have one more condition, like if x is greater than y or x is just equal to y. So in this case, we have more conditions. We can know this relation of x and y more specifically. So currently, we can say the relation is x is equal to y. And there's another simple way to use if and else, and you can read on your own. Another thing is we can use if statement, like inside another if statement. It's the same as when we use the for statement. We can use a for inside another for loop. So this if statement is, we can use another if else inside the statement in another if statement. So it can be, for example, here, this is the outside if statement. This is the condition x is less than y. And this print line, this line 5, is a statement. This statement can be one line or multiple lines. We can also include another if statement inside here. And we can also use a if statement like in the after else. So it's just depends on how you want to organize your conditions. So here, we first want to determine if x is less than y. If not, then we want to know if x is greater than y or is equal than y. So it's very similar to you use the else if, but the difference is this condition is like a more parallel relation. It will evaluate one by one until it finds a statement which is true. But this is, if this condition is false, it will evaluate another condition inside this one. So, okay, we can run this example. So because x equals 1 and y equals 1, in the if statement outside, we only know x is not less than y. And use another nested if statement, we are able to know x is actually equal to y. Okay, there's a practice you can write in your notebook. So basically, it asks you to implement a function fx, which add 1 to x if x is odd and positive.
By the way, she had to go.
What? Is
Zoom.
Okay, I see. Okay, we just give 1 minute. And we can do this together. So there's multiple answers we can solve this function. We can use like a first if statement. Here, if x is even, we usually use this one to say x is even, because this returns the remainder of x is divided by 2. So if x is even, the remainder will be 0. If it's odd, the remainder will always be 1. So
we can also write that, Lou, as remainder REM.
Oh, it's a function.
Yeah, so that might be a little easier for them. So parentheses, whoops, you put the parentheses in there, your
This.
x comma 2.
This one?
Yeah, and get rid of the other stuff.
Okay.
Yeah.
Okay.
Does that look a little more obvious for you? Just do the remainder function, please.
What happens when x is 0? Or, yeah, how do we account for x equals 0?
0 is counted as even. Yeah. So the question was, yeah, what's the remainder of 0 modulo 2, and the remainder would be 0. So 0 will be an even number. Okay, so we'll let you guys give them 3 or 4 minutes to type in their if statements. Ooh, can you nest all your if statements together? Nesting if statements.
Yeah, there's a self-check cell. If you're finished, you can run the cell.
So if x is even, you're going to return minus x. And if x is not even, then it's an odd number, and then you've got 2 different things to do.
Should I talk about?
Got a solution?
Yeah, so this question, you can use the nested if, or you can use if else. It will give you the same answer. Yeah, we can do this together. So it's more clear here to use a nested if, right? So if the remainder equals 0, then we can return negative x, or we can say x equals negative x. Then let's say else. Else, it means if you run the expressions here, that means the x is already evaluated to be odd. So here is another, you can use another if x is positive. If x is odd and positive, you can x equals x plus 1. Else. Okay. Here it, if x greater than 0, else x could be 0, but actually, if you run here, x is already no, it's an odd number, so it can't be 0. So the else is already only include the x is a negative number. Right now, x equals x divided by 2. Okay.
Why don't you put some comments like that else on line 8, put a comment next to it saying, okay.
X is even?
Yeah, x is even, and then the else. X is odd. You see, this helps you keep track of this is odd and positive.
Yeah.
See how that helps you go through the logic, and you can just check to see, is this really what you wanted to do? Trying to get all stylistically beautiful on us there. That's a hard code. That's a hardcore coder up there.
Okay, so everything check is correct. So far, any question on the if statement? Okay.
Could you do a quick solution if you started with the odd? I know, just open up a new cell and.
Okay.
That's tough, huh?
If x. Okay, so if this is odd, then there's another if. We can see here x is. Then if x is positive, okay, that's the same thing. Yeah, it's just changed the where you use the nested if. Okay.
Did that work out better when she did it with the odd? Because that was matching how the logic some people were, which, I mean, the problem statement first came, hey, if x is odd, do something like this. Cool.
Okay.
Questions for Lou from Zoomland? Anything?
No.
Oh, Zoomland is happy. Come on, guys, send her a hard question. Test her mettle.
Okay, let's talk about more on functions. So we've covered, we introduced function in previous labs, and this lab we're gonna talk about function more formally. So the function is very like the function we used in mathematics, which is actually a map from some input value to some output value. So in Julia, we use a function keyword, and at the end, also a return keyword to define our function. So here, for example, if it's a function name, you can use any name you want. You can also use some like some I don't know, special character as a name. You don't have to be a letter in Julia, but not in other languages. So here, I just use a simple like if as a function name, and inside the parentheses, that's the argument of a function, which is the input to this function. Here is the example. This function name is f, and the input argument is x, which returns the value x plus 1. So when we call this function, we want to, the syntax is we use the parentheses and we add the value to the argument. If you forgot to use the parentheses, it will be just a function object. You can also assign this function object to another like function. Right now, the g is the same function as if, so you can use g as a function name. So whenever you want to call the function, you have to use the parentheses and you give the value of the argument. Yeah, it's a very good programming practice to use the return keyword to specify which number you want to return. So there is a default value to return in a function, which is the last expression evaluated in a function, in a body of the function. But it's hard for people to read your code in that way. So usually we use the return to specify what you want to return in this function. Also, this return doesn't have to be in the last line in your code. But once it is executed, it will ignore the things below this line. For example, I have something x equals x minus 1. It won't be executed. Okay. So here, we can use the if statement inside the function, and which is a common way to use the if statement, actually. So in this case, we can use multiple return keyword. It will choose different value to return under different conditions. So here is a function to calculate the absolute value of the input number A. So we use a simple if statement. If A is greater or equal to 0, we just return A. Otherwise, we return the negative of A. And so in this case, even though we use multiple return keywords, but it only have one returned value, and it is based on the if statement. So we can also assign this returned value to another variable in our code. For example, give this absolute value to a variable called b. A function also can have multiple arguments. This is a function to get a sum of two variables. So here the input are two different numbers, or it could be the same number. So here, there's multiple arguments, but there's one returned value. It also could be there's a multiple returned value in a function. For example, there is a function we call max, which is you give an input vector, and it will return the maximum value inside that vector, as well as the corresponding index for that maximum value. So in order to do this, we will return two different values. The first is the value itself. The second one is the index of that value in this vector. Okay, this example is the function is as follows. We first set the maximum value as just the first element of that vector. And also we set the corresponding index as 1, means the first index. And we just look through the values in this vector one by one. Once we find a greater value, we set the maximum value to that value, and we also reset the index. And after this for loop will run through all the elements. And after this, we have the actual maximum value and the index. So we return this. And we can see this example is the A is a vector of 4 elements, 0, 1, 5, 3. And we give this vector to this function, it will return 2 values. The first one is the maximum value, 5, and its corresponding index, in this case, is 3. Yeah, this is just an example to how you want to return multiple value and why you want to return multiple value in your function. Any questions so far?
Hey Lou, I have a question, since nobody's asking the question. Your max function, what if you just say answer equals max of A? What's going to happen if you don't list both of the arguments on the left there?
Oh, you mean this?
Yeah. What's going to happen?
Yeah, that's a good question. It will return a tuple of those two values. Yeah, so right now the answer is a tuple of 2 elements, 5 and 3.
How would I access the 5 and then access the 3 from answer?
Yeah, you can use indexing. So the 5, okay, you can say answer equals the max A, and you can say maximum value equals answer 0.
Julia is a one-index language. So, Lou, you've been doing too much Python and C.
Oh, it's not. Oh, sorry. Okay. Yeah, I got it.
So sorry to do that to you, Lou, but it just helps everyone to understand that we have to practice these things to keep them going.
I think you can also do maybe maximum. Something like this. Okay, I'm not sure. Yeah, we can also just do this to get the two number.
Thank you.
No problem. And another practice, we want to implement a function, which is shown in this figure. This is actually a very famous, like the activation function in deep learning. Like in some neural network, the last layer is usually use some function like this to make the output value as a positive value. Also, it doesn't want to give you a value like very large. Yeah, so I'll give like 2 minutes to just use the if statement and return keywords to implement this function.
Ladies and gentlemen, and everyone else, start our keyboards, okay? Let's go.
Okay, is there a question? Do you want the other part? I think I'm done.
You have a question for me?
Yeah,
What is?
I think I'm done.
Well, you're going to walk them through this.
Okay.
Okay, so what's the logic here? If we just work from left to right, we first want to check if x is less than 0, then we return 0. Else if x is less than 6, we return x. And the last bucket, else catches everything, else return the value 6. End. Did I do it right, Lou?
I think so.
Accidents happen, guys, accidents happen. But that's just the logic. You just start from left on this function. Did you run the function and check it, the self-test?
Yeah, it's work.
Oh, I can't believe it. Okay, so this was, this will give you a forward substitution function. It's also in Julia homework 4, so we're not like giving anything away. But I would highly recommend you practice and build the backward substitution function. Now, the only thing I'm going to call out here, you can do it on your own at home, and then we can go through it, is you see there's a for loop that's counting upwards. And so remember, this line 10 means from I equals 2 to 1 in increments of 1. So there's an implied, because there's not a second colon with a 1 here, it's incrementing up. And if you're doing back substitution, 1 second, you want to go the other way. You want to start at the bottom and then work your way to the top. So if you have a for loop, you need to play with it a little bit. You want to be decrementing by -1. Okay, so that's the trick. Let me bring the mic over so we can help everybody here.
Yeah, I was just going to ask about that decrementing. I don't want to really give anything away, but I was going to ask, like, to confirm if my decrementing for the for loop was correct.
You have on the screen?
Yeah, just like that line.
So what we have here written on the screen is decrementing I goes from n minus 1, because the nth case would be done with the 1 here. So yeah, so you would have something like xn, b of n, u of 1 of nn, and then this would be from I equals n minus 1, decrementing by -1 and going to 2. And then you'd have a similar line here.
Well, it would go to 1.
Excuse me?
It would go to 1, though, instead of 2, because it's decrementing from n minus 1 to 1.
It would go to 1. Yeah, it's equivalent of n. I said that wrong. So the question was, when I said it was decrementing down to 2, no, it decrements to n, to 1, because we're going to start at n minus 1, which is the flip of 2. N minus 1 is 1 up. So you guys play with that a little bit. And come to office hours. We would love it. And this is just allowing you to play with and just see how quickly you can solve problems. Okay, peeling the onion. We've got 11 minutes, and then we'll take a break and let Tribby take over. So remember, the whole idea is to successively remove columns and rows from a matrix. And how can you forever forget peeling the onion after this GIF that Lou put in here for us, okay? So we want to build a first function that just takes one layer at a time. So Lou has built for us here the function peel one layer, peel one layer, and she's got it where you can do the layer equals k, okay? So this function, like we're doing in class on the simplified LU, where there's no need to swap rows in order to avoid a divide by 0, we boldly assume the pivot is never 0. So the way this method works is you look on the diagonal of your matrix. So those are where row and column are the same. You find that to be the pivot. You take the corresponding column, the kth column, normalize it. You take the kth row, and then you subtract it. Okay? So we've got, that's our function. We create it as example. Remove the first row and column, and look, bingo, bingo. And then just to emphasize that this peel command is general, it's not usually useful to jump to the third row and third column, but there's nothing to stop you from doing that, okay? This is, we took the pivot to be the 3-3 element of the matrix, and then we zeroed the third row and the third column. Okay, so that's how that the peeling the onion works. And it's very convenient to just put all that stuff and just make it into a single function. And then when you're doing LU, you want to first peel off the first row and column. Then you want to take that matrix after you've peeled off the first row and column, then you want to peel off the next row and the next column. And you can see by just taking k equals 1, and then k equals 2, and then k equals 3 and 4, you just systematically take apart the matrix. And then if you store the columns, that will get you your lower triangular matrix. And if you store the rows, you stack those up, that'll get you your upper triangular matrix. And then the matrix will be the product of L and U. So that's awesome. And so what we've done here is built a cell that successively peels off the function. So it goes from 1 to the number of rows. So we just take a copy of our matrix A, we get its size. For us, the matrix is square, so n row and n column is the same. Lou is showing us here 2 ways to initialize the L and the U to zeros, and then we're going to fill in the columns of L and the rows of U. You can declare L as a 0 matrix. Its elements are float 64, and it has n rows and n columns, because we've got those defined up here from temp, so it's going to be the same size as temp. Now, or another completely equivalent way, and you could have done this with L, you just say U equals 0 of temp. And if temp had integers, I think this would give you an integer 0, 0, 0. If temp has reals, it'll give you floating in it. But U will always be the same size as temp. So obviously, this is a very quick way to do it. And this is a more consistent way to always get the type at float 64. So it's kind of up to you. Okay, so once these matrices exist, we can then define their rows and their columns. And so Lou then just sticks this into a for loop. Her peel one layer function just calls it n row times and get the column, the row, and the new temp matrix, and just iterates. So this is the power of a for loop, okay? Instead of going k equals 1 and doing all this, and k equals 2 and k equals 3, you get it working once, and then bingo, this goes right to work for you, and you get the lower triangular matrix. This was the first column we peeled off. This was the second column, but because we'd already zeroed the first row and column, when we get this one, it has a 0 at the top. And when we get this column, we'd already zeroed the first 2 rows and 2 columns of the temp matrix. So this starts 1 level lower and 1 level lower and 1 level lower, and it has 1s on the diagonal because we've always normalized by the pivot. And then U is upper triangular. Here's the first row, R when we peeled. Temp now has 0s on the first row and the first column, and so when we peel off the next row, it automatically has a 0 here, and that's how we're building the triangular matrix. And then temp has 0s in the first 2 rows and two columns, and we get the new row. We get the new row, we get 1 more 0. We get the new row, we get 1 more 0. So we automatically build this matrix. And surprise, it's not perfectly 0. Not a surprise, we're doing numerical calculations. E to the minus 16, pretty close to 0 for me, okay? And so we've got 4 minutes. We'll let you play around with the Julia built-in function L for the LU decomposition. Once you have created your backward substitution function, and then you're going to have your own LU function in homework 4, you're solving a general linear system means LU factorization of the matrix A, solve Y equals forward substitute with L and B. This is AX equals B. And then you get X by backward substitution of U and Y. And yes, those functions exist in Julia, but on your drone, your small car, your Cassie robot, you may not have all of Julia because it takes up too much space. You've got to write your own very compact, fast code. And so now you guys understand what's under the hood, etc. Okay, so that's the idea. Lou, you want to finish this part? Turn on your mic. So she's got a new, oh wow, image.
Yeah, this is plot a clock of the current time. Yeah.
I'll just walk through it.
Yeah.
But I see cosine theta, sine theta, so that's going to get me a circle, or setting arrows at a certain spot. Okay. Let's see. I've run this one. Now I'm going to create a GIF. And so in project 1, you guys are going to create a GIF as well. And this takes a little bit because it's got 1,000 loops in it. And then while that's running, I'm just going to paste in. Whoops. Okay, so what's going on here, Lou? Ooh, it's getting almost 5:18, 19. I got to turn the floor over to Tribby in a few minutes. So that's what Lou was trying to let me know, that my time was running out. Okay, so she could have also built an hourglass, Lou, and had the sands running out at the bottom. Okay, that would have told me to get off the stage and let Tribby have it. Let's suppose you want to just play around and time your functions. I'm going to use the native LU function in Julia with a random 1,000 by 1,000 matrix. How long do you think it's going to take? How many think it's bigger than a minute? How many thinks it's less than a microsecond? How many thinks it's on the order of tens of milliseconds? Nobody wants to commit, okay? But you got a number, right? It took 35 milliseconds to LU factorize 1,000 by 1,000 matrix. If you added the back substitution and the forward substitution commands, those would take another 10 or 20 milliseconds. And so you've solved the whole problem in under 100 milliseconds, and it's AX equals B with A 1,000, okay? Is that better than you could do in high school? Is that better than you can do in Math 214 for some of you who've been through Math 214? Yes, it kills it, okay? It just kills it. So it's just a simple way to do timing. I was checking on the tick and tock commands that used to exist in Julia, and I've read that they've been deprecated. So I don't know if they've actually come back, Tribby, or not. But this is another way to get the time. Now I ran my own LU function on this, and it was more like 7 seconds, okay? So I've got some better programming to do to go from 7 seconds to 35 milliseconds. So Tribby, how fast can you and I get if we work together on this? Can we get it under a second? I don't know. Okay, we're done here. I'll be happy to answer questions. Everyone online, we're going to take a break. Let Tribby come up here, hook up her computer. I'm going to disconnect. And hope you've had another fun day in Rob 101 Lab and picked up some good skills. Thank you for the clock, Lou.
Okay. So today we're going to solve for a linear system of equations, ax equals b, using LU decomposition. And we're going to look into two examples. One is you're trying to solve this circuit using Kirchhoff's law. If you're interested, we'll take this one. The other one is solving for transformations. So I'm going to give you two squares. One is the blue one is the red one. And then we're going to try to find a transformation matrix that can take the blue square to the red square. So instead of, if you've started project one, we give you a transformation matrix, and then you just apply it, and you're able to transform one square into the another. In here, we're not going to give you the matrix. We're going to have you find it using LU factorization. And then finally, we're going to code the transformations example in the Julia notebook and write down functions for forward and backward substitution and how to calculate LU. I also think we're not going to have a lot of, so let's do this. For the first circuit problem, I'm going to break it down into LU, and we'll compare if we have the right answers. And then for the second one, we're just going to start coding instead of writing down our own LU factorization. So who here is not familiar with Kirchhoff's circuit rule? I think it's called. What's it called? It's been a while. Kirchhoff's circuit law? The one where like the current that passes through, like current on the junction doesn't go anywhere. Junction rule, yes. We're good with that. I guess you guys are better at this stuff than I am even. So we applied those equations and we got, well, for the junction, we have it right. What's that other law where, okay, forget that. Do we understand how these equations come about? Because I don't remember the name of the law that does this. From like this loop, and then this loop, and then this loop. Yeah? These make sense? Minus 5I1 in the first circuit, minus 6I2, minus 3I1 plus 2 equals 0 from the first one. Say yes. Okay. So we have this set of equation. We want to convert it into AX equals B format. So let's do one thing. We have X, we're going to say is our unknowns is I1, I2, I3. Can you tell me what A will be? Yeah.
-5, -6, -3,
-8 in the first one, right? So, well, maybe this is easier. So rearrange the terms, which we did not do here, okay. So yeah, -8, -6, and 0, right?
and then -2,
Mm-hmm.
8, yeah, -5.
-8 and -5, yep.
And then -10, +10, and 15.
Yep, yep, that's correct. For the second one, should it just, it should just be 8, you think? Oh, yeah. Yep, yep, okay. And what is B? Mm-hmm. Yep. Okay. So we have a set of equations ax equals b, and a doesn't fit into the triangular setup just yet, right? And we don't want to find the inverse of a like you would, because I think we were trying to get to it in the lab section, but if you actually time it, for a 3x3 system, you wouldn't be able to see. When you find out the inverse of A, and then you just calculate B is equal to inverse of A times X is equal to inverse of A times B. And then you compare it to how we do it with LU, you'll see there's a considerable difference in the computation time, which is why we learn LU factorization, because when you're working with really big point clouds and stuff like that, calculating inverses is just not going to work. So for a 3x3, it's not as convincing, but it's easier to do hand computations for 3x3, right? Now, do we want to sit down and calculate this, or have you guys finished homework and you're very comfortable with how to calculate L and U? Anyone struggling with it? Because we can go over it quickly. No? We know how to find R1. Yes? Yeah, for sure. So for LU factorization, what we're trying to do is we're trying to factorize our matrix A in a way that it is a lower triangular matrix and an upper triangular matrix. The way we build our matrices is the lower triangular matrix is a collection of columns, and we'll see how to find these columns, but for now, take my word, there's some columns C1, C2, C3 that I found, and a U matrix is a row. I'm going to represent it as a bunch of rows. It's still like each column is 3, so it's still 3x3. Does that make sense? Yeah. And then for each row also, there's 3 elements in the row, so the U is also a 3x3 matrix, right? So I'm trying to decompose my A matrix as L times U, where L and U are these things. And now I'm going to make a case that my A equals C1 R1 plus C2 R2 plus C3 R3. Does that make sense? Do you guys remember the column multiplied with row formulation of matrix multiplication, right? So these two things are comparable from our knowledge, right? We did how to multiply 2 rows. We got column times rows. It gives you the final multiplication. So this is equal to LU, right? We're good? So what is left for us to do is to find these R1, C1, R2, C2. Now, how do we get that? So for C1, we're told take the first column of A and divide it by the first element of A, right? For this problem, what is the first column of A? -8 by all those things. I'm gonna divide it. Looks like we have. Okay. So C1 is gonna come out to be, it's 8, so divided by -8, so 1, 1 by 4, 5 by 2, right? From here. So take the first column, divide it by -8. I think that's what you're gonna get. And then for row 1, just take the first row of A. And that gives you -8, -6, 0. Oh, yeah. 10 by 8. Yes, it should be 5 by 4. Yep. Let me correct that. Now what's left to do is I'm going to consider a temp matrix, which is A minus C1 R1, and I'm going to assume that it's equal to C2 R2 plus C3 R3. Does that make sense? And one thing you want to notice here is we want the first and the second column and row of our temp matrix to be 0, right? Because everything on the right side is like C2, R2, C3, R3. It's all going to be like, it'll all be here. It's C2, R2, right? So all of this should be 0, and then whatever's left here should come from here, correct? So let's see if the CR we got actually cancels it out. So my A matrix, I'm going to copy it. It is -8, -6, -10. Copied it wrong. -8, -2, -6, 8, 10. This is not clear. We're going to publish like proper solutions so you don't have to copy this. And my handwriting is terrible. So it'll be not handwritten. And 0, -5, 15, minus C times R. So C is, hold on, okay. -8, -6, 0. So the first row is the same. That's how you always cancel out the first row. Then second one is -2, -3 by 2. Yeah, and 0, and then 5 by 4. Yeah, and then 5 by 4 times. Okay. 5 by 4 times -8 is -8. minus 10, and then something here. I don't know what that is. So we note that this, and then this row, and this column and this row will cancel out, and we will get something in this box right here, right? That's what's going to be left. And then you keep doing it, and you find C2, R2, C3, R3, and you're left with like an LU matrix, and then you're able to say that A is L times U, correct? Now that we know how to do it, are we clear on how to use it? Sorry, yes? What do you do after you get L and U? So remember we were trying to solve AX equals B, right? And we were like, we don't want to use the inverse function. Like, I don't want to invert A and then multiply with B to get X, right? What I want to do is I want to use forward and backward substitution, because that's easier. But to do forward and backward substitution, I know I need triangular matrices, right? Because I can do backward substitution only if I have an upward triangular matrix, right? So my workaround is I'm going to factorize A into triangular matrices. So that's what we found, right? We found A to be equal to L times U. So I replace LU here in my system of equations, and this is my new system of equations, right? Now, to fully solve my system, I'm going to call this to be Y. Does that make sense? So I'm going to break this down into solving L times Y equals B, and U times X equals Y. Does that make sense? It's like a change of variable, right? Good? So then what would you use here? Which method? L is the lower triangular, yes. So how would you find the solution? What's the method here? Forward, yep. So this would be forward substitution to find what's our unknown here? Y, right? And now in this part, now I already know Y, right? I found it. Now I'm trying to find X, and we will do, because it's upper triangular matrix, we're going to do backward substitution. Right? This pipeline is clear. As soon as I give you AX equals B, you're going to be like, I don't want to use inverse. And you go into LU, and you're able to solve it with forward and backward. Yeah, no problem. And Jesse's telling me we did peeling the onion in lab today. So I guess you guys already know how to find out the different layers, R1, C1, all of that. So I'm going to let you guys find, did anyone sit down and find the L and U for this, or do we just want to move on to the next one? Nobody feels like writing it down. What's the consensus? No? Next one? Okay. I'll just, you'll find the solutions online. I'll post it after recitation, and try to solve it by yourself. See if you can find out an X and a Y. And then see your X is going to be your currents in your circuit law. So this is what you're looking for. And if I have the right solution, it is not a very clean answer. I'll post it, but try to solve it for yourself. Okay. So if we actually went through that whole thing, you would have solved it without any row permutations, because that's just how the problem was set up. But like we've looked at in lecture, a lot of the times we need to permute rows to actually avoid dividing by zeros. Because every time you have to divide by zero, there isn't going to be, you can't, like we're stuck on that step. So we're going to take an example on how to do LU decomposition with permutations. And I thought it'd be interesting if we took up the squares thing from project 1. So what we're going to do here is I've given you a blue square, and there's 4 points that I'm using to plot the square. The points are right here, right? So this point is 2, 2. This is -2, 2. This would be 2, -2. This is -2, -2. And we just use that to plot our square. And then I give you another square, which is rotated. And you're going to have to believe me that it's the same square. And how do you calculate this diagonal? This should be, doesn't matter, but what if I just told you that this was 0, 2, √2. This is -2 √2, 0. And what is the point here? 0, -2 √2 and 2 √2, 0. Does that make sense? The diagonal is like that because I took the blue square and I rotated it like that. So the diagonal is now on the x and y axis. Now, if you've looked at the code in project 1, where we're transforming the square around either translations or rotations or scaling, we've been able to say, we've been trying to find a transformation such that I find a matrix A, multiply it with my points, x and y for now. Actually, I want to start from blue. So some matrix T that we've given you for now, but we're going to find it here. Some matrix T, some points in my frame x and y, give me points in my other thing, x and y in red. Is that something we've seen before? Is this new? Is it exciting? So the way we set it up in project 1, we told you about these point clouds. Why is this important? Let's get that first, right, before we get into it. And I'm going to prove that this is a linear operation. But why is it important? So we have a LiDAR, right? And there's points that it's noticed around it. And we saw it in the demo also. There was like this colors on the points giving the intensity. It was all very exciting. And then we were asked, so now the LiDAR is on you. You're holding it. You're the robot. And you start walking around with it. But the observer needs a common frame, right? So if I'm sitting here, you're the robot, everything is in my frame of reference because I'm observing it. I want to make sense of what you're seeing when you're walking around as a robot. So whatever you're seeing is in your frame of reference, right? So you're describing to me that the wall is 2 meters away from you, in front of you. For me, it has to be the wall is 2 meters away, and then you're 5 meters away, so the wall is essentially 7 meters away. And all that's basically a translation, right? And if you look at how we work through the translation in the project, we convince you that it's a linear transformation, and so is rotation. Here, we're going to find the rotation between these two squares. So without going into the homogeneous transformation, which is what you're supposed to do, I'm going to argue that there is some A, B, C, D, some transformation matrix that can take the blue square to the red square. And your job is to find that T, right? So let's break it down. My matrix of unknowns now here, so the system of equations is basically some, I want the blue. A times x plus b times y is x in the other coordinate frame, and then c times x plus d times y is the y coordinate in that other frame. Now, we want to bring it into the standard ax equals b form. Excuse the notation, because like x is repetitive, and I'm also saying it's the point, but some x tilde, let's say. What would x tilde be? What is our unknowns? What are we trying to find? We already know the points. Blue x and blue y are the coordinates, right? We're trying to find, it's a little, it's not intuitive, and you'd see there's not enough equations, but I'll show you how there's enough equations there. Yes? Yeah, we're trying to find the transformation matrix T, this one right here, right? Which is A, B, C, D. These are our unknowns, correct? We're following? Make sense? Because you have to break away from, it's not always going to be like, if there's x and y, those are unknowns. You have to see what you're actually finding, right? Yes?
Don't we know what x and b are? Because at least in the form that we know what the variable, or we have points that we can look at. So don't we, I'm confused why we're solving for that weird x thing.
So the question is, don't we know what x and b are? That's correct, because my notation is a little confusing, but this is a new x and this is a new b. Just like here, x tilde would mean everything that is unknown. So x tilde would be bringing it into the standard formation is what I want to do, where x and y are still the coordinates. So x tilde would be the unknowns. So what are we trying to find?
Then what would A be and what would B be?
We'll have to find what A and B will be. So the question is, what will A be and what will the new B tilde be, right? That's where the points come in. So if I write this equation down and I put in specific instances of these points, so I'm going to talk about correspondences between this point, and then this point and this point, right? Let's see how we can break it down and bring it into a standard format. So this equation, if I put in x and y, this becomes, so blue points, 2 times a minus 2 times y equals the correspondent point right here. What is the x coordinate? 2 root 2. Does that equation make sense?
Would it be 2a minus 2b instead of y?
Oh, yeah. Yeah, you caught me. Perfect. Yep, 2a minus 2b is 2 root 2. Does that make sense?
Yeah, I get it now.
Yeah, yeah. Yeah, it's a little... And then similarly, you'll write for the same point, 2a, 2c minus 2d will equal 0. Agreed? Now, I also know that I have 4 unknowns, right? And we have a lot of points, but we're just going to look at 2 points, and I'm going to argue just by finding the transformation between those 2 points is enough, because the square is consistent. If the square was broken, like if it wasn't the same square, you would have to find, is this confusing?
No.
Tell me now. Okay. So
it'll give you 2 more equations with all 4 of those variables again, so then you'll have 4 equations with 4 variables.
exactly. So for a square, if I tell you 2 points, right? 1 point, and like if I give you a line, you're able to find a square uniquely, right? Okay, so I need 2 more points here to find, to have 4 equations to solve A and B. So I'm going to use this other point, which is 2, 2, so 2A plus 2B and 2C plus 2D. Get the correspondence here, which is this point right here. So this point and this point is what we're getting for. The x coordinate is 0. The y coordinate is 2 root 2. Make sense? Did I lose anyone? No? Okay, if we know how to solve this, now we're set to, we have this ax tilde equals b tilde format. And now what's left to do is to just find x tilde, which is this transformation matrix we're looking for. So our A matrix, what will be A? X tilde is A, B, C, D. What is A and what is B? Anyone? Yeah.
It'd be 2, like the first row would be 2, -2, 0, 0. And then it would be 0, 0, 2, -2.
Let me get that. Yeah. 0, 0, 2, -2. Yep.
2, 2, 0, 0.
2, 2, 0, 0. 0, 0, 2, 2.
And then 2, red 2, 0, 0, 2, 2.
Perfect. Agreed? Now, next thing will be, we have ax tilde equals b tilde. We have this. Now we know we're going to solve for the transformation matrix, x tilde. And I don't want to do it by hand, so we're going to do it on Julia. Are we ready for that? Yes? Excited? Ready? Happy? Okay, very good. Let's Let's go to Julia. So we have our square, we have the other square, and you should be able to see that it's the same set of equations. It may just be the order of equations is different, so your A and B are permuted different, but you should be able to compare that we got the same answer. And this is worked out here for us if you want to look into it. So we have an A matrix here. I wrote it down. Let's first see. Okay. Let's use this is what we had, right? Maybe some permutations, but that's what we had. We had 2 points, 2, 2, and 2 and -2. They're both in here. And B is this. Two root 2 is 2.8 something. So we have A and B. We need to find the LU factorization. Are we good with the code, or do you want to code this with me? Do you just want to use the LU functions in Julia? Yeah? Nobody wants to do it? Nobody wants to peel the onion? Hurts your eyes? That makes sense. I'm still going to make you do it. No? Okay. We're not interested. We're just going to use the LU function. Is that okay? Okay. If anyone does want to go over the code for LU factorization with me, either say now or I can talk later also. Anyone interested in that? Going over writing LU? No? Already covered in lab? Is that it? Yeah? Okay. So Professor Grizzle already covered it, so we don't need a revision. Okay. We're going to use the LU function, and using A, it says LU not defined because I did not run this cell. So for the A matrix we had, we should be able to see it also. For an A matrix like this, you want to be able to permute the second and the third row. Does that make sense why? Just looking at it, you can tell? Because you never want the 0 in the diagonal. Yes? Yeah, sorry, I answered for you. I'm sorry. So yeah, if you look at your matrix and it's of this very simple form, you should look at it and just be like, there's a 0 in the diagonal and I can fix it if I just swap the first and the second row, the second and the third row, which is what Julia did for you. So if you look at the permutation matrix, you take the identity matrix and then we swapped the second and the third row, and that's what your P matrix is. Then finally, this is your L, and then this is your U matrix. Now that we have that, we know what we need to do, right? We need to find, once we have P, A times X is P times B, does this formulation make sense to you? Is this is the same as AX equals B, right? We're not changing our system, we just multiply it with the P matrix. Correct? And we found that for a matrix with permutation, P times A equals L times U. Right? We agree that that's true? Not cheating? Yes. Okay. Then this can be written as L times U times X equals P times B. Correct? And it may just be easier if I make this a B dash, and then it's exactly the same problem as before, right? Then it's this thing, but just you're doing a B dash. Correct? And B dash is P times B. Yes?
I found out that so the question doesn't exactly relate to what we're doing, but with the permutation, if it's not, what happens if it's not possible to get a non-zero in the diagonal? Or to, yeah, is it, what happens if it's not possible to get no zeros in the diagonal?
So yes. So the question is, what happens if you can't get a non-zero in the diagonal? So let's see. I'm going to change my A matrix in a way that you're not going to be able to eliminate the diagonal. I need to look at the form to actually for it to make sense. Okay, I'm going to take out the last. I'm going to make it. Where did myself go? Right here. Let's see what this looks like. So you can arrange it many different ways, but you're not going to be able to get rid of the zeros in the diagonal, right?
I think you can.
Yeah, you still can, if you swap.
If you take the 2 out of the second row, but put the 2 back in the other one.
The third row can become the second row, and the second row can become the third row. And the
If
third
you just
row.
take
Oh, okay, yeah. Well, we don't have to even do it, but if there is something like that, you already know that there isn't a unique solution because the determinant is 0.
Okay.
Correct? But even for this, you'd be like, if I try to do LU of A, oh, that would work. Okay, you're right then. Yeah.
Okay, but that makes sense.
But yeah, once we actually go into it, you're going to look into how looking at LU can also tell you if there's infinite solutions or if there's no solution. And that's way into like linear independence, and after all of that, we go into it. For now, take my word, if I tell you, we're not going to give you like bad matrices to do LU on, okay?
Thank you.
No problem. Okay, so now we know what this is. I'm just going to rename my variables, and we're going to solve for it. So my L is, I called it L2 for some reason. U is U2 for some reason. And then my B is P times B, which is bad coding. So I'm going to call this B dash, B bar. Right? And then now we're going to solve for the variable, the transformation matrix, which is X. So first, I'm going to find Y using forward substitution of for L times Y equals P times B. Yes? And I'm going to use a different code. I'm going to use the homework 3 code, basically, instead of the homework 4 code that you saw in lab today. So in homework 3, we started with zeros, and then we said for I equals 1 to n, I said y of I equals b of I minus a of I comma this transpose into x, and then we're going to take the first element. Does anyone remember this formula? Is it just me? We broke this down last time on why this is the way it is. Do you remember? Yeah? Why we had to initialize y with zeros and all of that. Okay. Let's see. And I was wrong. Wait, I'll have to look at my solutions. Probably got a bracket wrong here and there. Ooh, called it A, should have called it Y. I'm just gonna copy it. Basically, I had A instead of L because I don't know why I did that. Do we remember this? We had, I think in the homework, you run through it, but you probably never write down the for loop for it, or do you? Maybe there is. There's in one part where you write down a for loop and you do forward substitution, right? Yeah? So this should give us 0, 2 root 2, 2 root 2, minus 2 root 2. Is this confusing anyone from last recitation? Or from what you've seen in homework 3? This thing, this mess right here. Make sense? Yes. Okay, we're ready to move on. We've seen this. Okay, so we found the forward substitution. Do we know how to do backward substitution? If I tell you this, and this was our formula from last time, we're getting a general form of xn to x1, and we're going to go like this. Would the same thing work if I just go back to up? Yeah? What do you guys think? So for k equals n, and I'm starting with x equals all zeros. X of n would be b of n minus, you remember, kth column of A, kth row of A transposed into a column vector. Multiplied with x, which is for now all zeros. So that whole term becomes 0 divided by A of n comma n. So it's true for k equals n. Is it true for the general form? What about x1? This is b1 minus, by x1, at the 1th iteration, what would my x vector have looked like if I did this n times? So I have xn all the way up to x2, correct? And then this, I don't know, I'm trying to find, right? And then the kth row, so the first row of A multiplied by x, would that give us this term right here? Yeah? It will be we're agreeing, I see. So the formula stays true, but we go from n to 1, right? So how would we write it in code? And I think you have a different thing going on in, this isn't the best way to do it, right? You're going to do it in homework 4 properly, where you're not doing the initialization with 0 thing. Don't do it. But for now, I'm going to find xk. I'm going to go from n to 1. This b will be y.
Do you have to define a step, or will it just?
Say that again?
Do we have to define like a step? Like n colon -1 colon 1?
Oh, yes. Yeah, we're going from n to 1. So we need a step size of -1. Good catch. And yk, this matrix is u, right? Agreed, because we're solving for ux equals y now. Right? This will be x, u. Does this make sense? Yes? Yes? What do you think we'll get? So I'm going to tell you that this is 1 by square root of 2. Right? So this matrix you see right here is this matrix you see right here is actually 1 by under root 2 minus 1 by root 2, 1 by root 2, 1 by root 2. Oh, plus minus, because we changed the second and third column. This is your transformation matrix. Just writing down T. Yes? Yes. And once you actually read the homework, you will see that for rotation, and we tell you this, the formula is sine theta cosine theta minus cosine theta? Sine theta? I remember that, I think so, right? And here you put theta is 45 degrees, because how much did we rotate our square? It was like this, and it went like that, 45 degrees, right? Does it make sense? Hence proved that we weren't tricking you. That is the